Welcome back to day 5 of the 2024 Advent of Code. Let's get straight into today's problem. So we're doing some safety manual updates, and we have some protocols that specify that the safety manuals have to be printed in a specific order. Specifically, we're going to get a bunch of lines with two numbers separated by a pipe telling us that the first number's page must come at some point before the second page number. We have two sections to our input: the page ordering rules and the pages in each update. The first section tells us the rules one per line. So for example, the first one tells us that page 47 has to be printed before page 53, although it doesn't need to come immediately before. Then we get our page updates, and for part 1 to start, we're going to need to figure out which updates are in the right order. So for example, the first one's in the right order. If we go through the page ordering rules, we can see that all of the pages are ordered correctly. Going through to here, we can see that the output we want is to get the sum of the middle page number from each correctly ordered update. A bit of a weird format, but let's get straight into coding. So for this problem, let's start by grabbing our input. We're going to use open0 as usual, and we're going to assign it to a variable. And the reason I'm doing that is because we're going to need to loop through it twice. And if I were to do for line in open0 and do that twice, that would not be allowed, because after you open a file, you can't open it again until you close it. And I could close it, but that would require me to assign it to a variable, or I'd have to do like with open0 as file. And in either case, it's easier to just do it this way. So that way I only have to open it once, and I can just run two loops through it. And so the way I'm going to do this is, let's store a list of the rules. For each line, if the line is white space, then we can exit out of the loop. Otherwise, the line will be two numbers separated by pipe. So we can add that to the rules by mapping int over the line split by the pipe. And so if we print out the rules, we can see that we've read out each of the page ordering rules. For the rest of the lines, we will have them in the format of a comma separated list of integers. So if we do that, we can see that we have our lists of integers, and now we need to check if they're in the correct order. Since we're going to be doing a lot of comparisons, let's write this into a function. And so what we can actually do is we can pre-process the rules here. And so what we can do is we can say cache is going to be a map from a pair of integers to whether or not it's in the correct order. And so we're going to do for x, y in rules, cache xy equals true, cache yx equals false. And if it's not in the cache, then it means that it doesn't have a particular ordering that's required. And so what we can now do is we can say for I in range length of update, for j in range I plus 1 up to the length of the update. What we're basically doing here is we're running two pointers through the list to look at every pair of elements, where I will always be strictly less than j. And so because we need all of our pages to be in order, and we can't just check pairs in case we have any uncompared pages or any errors in the input, for example, just in case they're coding in any malicious input, we can catch those and make sure that every pair of pages is in order. And so we need cache update I, update j to be true. Now it could also not be in this map, and so what we're going to do is we're going to say key equals this pair, which is the pair of our pages. And if key is in cache, meaning that it is a rule, and the cache entry is false, telling us that those two pages are out of order, then we can break out of our loop. Now we actually want to continue this loop. So we want to break out of both of these loops, but that's a bit difficult to do. So let's make a function called isOrdered. And we can take this, move it here, and then we can exit the function by returning false. At the end, if we've checked every pair of pages and they're all in order, then we can do return true. So now we can say if is ordered update, we can add to a total its middle element. To get its middle element, we need to find the item at half of its length. So let's suppose we have a list of 5 numbers. Its length will be 5. And so when we divide that by 2, we get 2.5. If we round this down, we'll get 2, which is the index of the middle element. So we need to have the list's length and round it down. We can do this using the Python / operator, which is floor integer division, and it will take the quotient and floor it. So we can do total plus equals update at index of length update floor divided by 2. At the end, we just print out the total to get our answer for part 1. Now for part 2, as may not be entirely surprising, we need to sort the incorrectly ordered updates. And once we have only the incorrectly ordered updates, so we can ignore the updates from part 1, we again need to grab the middle page numbers of the fixed ordering and sum those to get our answer for part 2. And so what we can do now is, if is ordered update, we can skip over this item and continue. And now we need to sort update by our system. So what we can do here is we'll update this a bit, and I'll explain on my whiteboard here. So what we're going to do is we're going to do comparison-based sorting. In comparison-based sorting, essentially what we do is we have 2 arbitrary objects, and we have some function that takes in those 2 objects and gives out some number. If the number is -1, then it means that they're in the correct order. If they're 0, it means that they're the same, which means that they may be reordered based on other factors, such as other elements that might have a particular ordering. And if it's 1, it means that they're out of order. The intuitive way to remember this is, imagine these are numbers. If x and y are numbers, then the default comparator for sorting integers is x minus y. And now this sorts them forward, so we can imagine if x and y are in order, then x is less than y, which means that the output will be negative. If they're not in order, then x will be greater than y, meaning that our output will be 1. And if x and y are equal or uncomparable, then we return the only remaining option of 0. So essentially, if they're in order, we get -1, and if they're out of order, we get 1. So now we can say, instead of not cache key, it'll be if cache key is equal to 1, matching this for out of order. And so if we try this again, we'll still get the correct answer for part 1. And so now we can continue, and then we'll do update.sort, and we need a key. Now here's the thing, in Python you actually don't have sorting by comparator by default using just the sort function, you only get a key. With key-based sorting, what we're doing is essentially each object has a function that maps it to some number. For example, like this would cause these 2 elements to be swapped by the sort function. The problem is that doesn't work here, where these 2 objects don't have any inherent value and are rather defined using a comparator-based ordering. Python fixes this by having something in the functools module called cmp2key. What cmp2key does is exactly what you might expect. It takes a comparator and it converts it into a key function. I'll briefly explain why this works at the end of the video, so stick around if you're interested. We need to have some comparator function, so let's define it over here. So we'll define a comparator that will take 2 values x and y and return their comparison. To do that, we just need to take hash x, y, which will be -1 if they're in order and 1 if they're out of order, exactly as I said we needed. Now, this could run into the issue of the particular ordering not being defined within the input, in which case we can do cache.get, and then we can provide a default value. In this case, our default value will be 0. This prevents it from erroring and returns 0 out of the comparator if they're not comparable, which is correct for the purposes of sorting. So we take our comparator function, use the magic function to convert it into a key, sort our updates, and then do the exact same thing as before. Total plus equals update at index length, floor divided by 2. And that gives us the correct answer for part 2. Out of curiosity, let's see what happens if we assume that all of our pages are in the listing. Okay, so it would appear that the input is indeed comprehensive and every possible pair of pages is represented in the ordering scheme. However, just for safety, I did not want to assume that here. So now let's briefly go over this magic comparator to key function. What exactly is it doing, and how can we even do this when I just said that our values don't have any inherent numerical value and have to be ordered based on a comparator? Well, the way it works is via something known as operator overloading. Essentially, in some languages such as Python, you can override the functionality of certain operators. The way Python's sorting works internally is actually comparator-based and not key-based. I kind of find it weird that we need to use this CMP to key function instead of Python just having a comparator thing in their sorting algorithm. But I don't exactly know how the internals of the sorting algorithm works. So let's take a look at this. The double underscore followed by a name followed by a double underscore is known as a magic function in Python. Essentially, these are functions that have behaviors outside of just being a method name. For example, you are probably familiar with double underscore init. This is the constructor for the class. And so here we have a class called K, which is just a placeholder name, and it has a initializer of setting its slot called object to the thing that you pass in. And so we see that CMP to key takes a comparator and returns a class. And because classes can be called like functions, because in Python, if you have a class, you can just call it like a function. We see here that this calls the constructor function and returns an A object. That means that what CMP to key is doing is it's returning a function-like thing that takes an object as its parameter for the constructor. And because key is a key function, meaning it takes each object in the list and returns some comparable object, which I said were numbers, but that's actually not entirely true. What that means is that our key function is now the constructor for K, meaning that each of those functions, each of the objects in our list will be mapped using K. So what do these functions do? This is the less than function. If self is less than other, that means that the comparator will say that self comes before other, or in other words, it will be less than 0. So what this does is basically we've created a magic object that doesn't actually have any inherent numeric value. It just knows what it's supposed to represent. And when we ask it if it's less than another object, which we assume is going to be of type K, then it will simply just ask the comparator whether it's less than the other element. Likewise, it is greater than another object if the comparator says that they're out of order. In other words, the comparison is greater than 0. Similar for all other things, they're equal if the comparator says it's 0. It's less than or equal to if the comparator says it's less than or equal to 0. And finally, it's greater than or equal to something else if the comparator says it's greater than or equal to 0. Finally, hash is set to none. This is just a thing to circumvent issues when dealing with caching and map keys and stuff to prevent internal functions from trying to hash and cache the value of this K object, which could cause issues. So that's essentially how this works. It creates a class that doesn't actually have an inherent numeric value and simply just overwrites all of its comparison operators with other objects by referring to the comparator. So it kind of cheats around the whole you need a key function system by keying each object to a wrapped object k, which then defers the comparison functions over to the comparator. So that's how this works, and that's how I chose to solve this problem. You could do this in a variety of other ways, but this is the way I found to be the most simple, and I figured I'd throw in an explanation just so you understand what exactly is going on, and it's not just pure magic. In any case, thank you for watching this video, and I'll see you tomorrow.